delve into it in a non-PPR league,
Non-PPR?
and I had alpha more or less.
Yeah, but one of is non-PPR.
So it's just like,
Well, thanks for coming and keeping your intentions and effort toward this course. So, again, congratulations with successfully completing your first assignment of presentations on what were you presenting? Yeah, postulates of quantum theory. So in this course, we are targeting one of two branches of chemistry, synthesis and characterization. So we do not deal with synthesis, we deal with background for characterization, and there will be no experiments, there will be only theoretical backgrounds for understanding how the measurements are going on and what can be measured and assessed through apparatus. Since molecules involve electrons that move so quickly that they obey wave nature, we need to fight strong to get through wave electron. And last time when you were presenting postulates of quantum mechanics, you basically covered everything one needs to be little wizards, to predict future of electrons developing in time in the molecule, predicting any stationary states and dynamics of molecules, and anything one can measure related to molecules and materials. But these fundamental statements that you have presented were correct, but right now we are missing practical part, how to implement them and how to connect them to real life. So it will take another about 75% of the semester until the end, and it will be it's hard work. So if you are anticipating of missing some meetings, here is a list of the course program from previous year, and above this line it is this year, so you can watch recordings of the meetings in the YouTube. And today we are starting to approach closer to practical aspects of describing properties of characterizing molecules, materials, or maybe we will start with somewhat simplified objects. This is a very long path, so do not expect immediate success and quick rally, because if we skim through and overview major conclusions, you will be aware enough to what can happen, but you will not be able to do things yourself. So we better go slowly but surely with little details. So also, I was promising you once that we will try to avoid homeworks, but once you will be entertained with them. So it's time. So it will be homework offered right now with due date next Monday in class. This one is not very complicated, and it overviews the background from the math and classical mechanics. But if you get through this assignment easy and quickly, then the rest of the course will be not very challenging. So it relates to our first few meetings. So lecture material goes ahead of the homework. So first two assignments, first three problems total. So first two deal with non-quantum properties of classical objects that just move straight or on some trajectory. And if you feel comfortable answering some simple calculational questions, then you appreciate simplicity of classical things, and then you will enjoy how powerful you become in describing much more complicated wave nature. And the third question deals with one of the simplest examples of wave nature, the superposition of waves without describing what is their where these waves are come from, and are they waves of tide, acoustic, electromagnetic, or electronic, just mathematical processing of conversion traveling waves into standing waves. Also, I was promising to give you a little summary of mathematical operations that probably you all are masters in through your calculus and differential equations. But especially the first 4 lines of this chart will help you to solve the problem number 3 with no trouble. So I think it's about 90 minutes maximum to do this homework. If you're confident and if you were doing something in before, something similar, potentially one can do it in 6 minutes. But in 90 minutes guaranteed. So do not worry. Okay, so here is your homework. And here is the last slide of today's meeting where you arrive. So if you are confident and familiar through this material, you can stand up. Some of these aspects, so I will just provide details for last 2 lines. If they create, if they establish a new challenge for you, then it means that postulates of quantum mechanics were sufficient. So everything we will be doing just follows from this logical statements you already described just now. So the broader goal of the course is to get background for characterization branch of chemistry. The very narrow goal of the course that you shouldn't declare in public, just to yourself, is to predict future of an electron, of an object that holds wavy nature. And we already got 2 ways to predict. So this wavy nature of electron is recorded in wave function, right, which depends both on space coordinates and time coordinate. And one can travel from past to the future either in form of evolution operators. One always need to formulate the operator. So this is important as a background, but it is not used in solution of majority of practical problems. The second way is propagating forward to from the past to the future by the infinitesimal, very small time step. So if you have wave function in the past at time t, you can develop wave function at time t plus delta t by multiplying this wave function by this step. Right? You have made some numbers. And one of them is your favorite entertainment called homework. So this one is very practical, is very helpful if you decide to solve physical chemistry and quantum mechanics problems with computation. So everything with finite differences, delta t is designed for computation. But if you are having just academic interest to pass this course, solve some problems, and get your credit and go further to the experimental track, industrial track, if it is not goal of your life, this is most canonical academic way to solve for propagation of the wave. So it is a general way for solving which equation? Starts with letter S.
Schrodinger's.
Yes. And you were asking one of your questions previous meeting deals with this stuff. You recognize this as it goes through. So the equation here that we will go over through the rest of the class is also a way to propagate wave function of electron from the past to the future. So here is the wave function in the past at time t equals 0, and here is the wave function at future at time t. Right? So this is initial condition, and the only thing to solve this problem is operator of energy, Hamiltonian operator. It doesn't show up in this construction, but it is implicitly hidden there. So this is sort of summary and prescription how to predict the future. In fact, between these lines or behind these lines, there is a return from time-dependent Schrodinger equation into time-independent, right? Finding the eigenfunctions and eigenenergies, and then finding projections. The proportion, how much the initial condition is composed of these eigenstates. Do not think about it right now. It is too much. I will go slowly but surely. But if you do have this projection here, wave functions and eigenenergies, and here you can propagate and find future any moment of time. This is not purely philosophical or academic knowledge just for memorizing and reproducing. We will follow this prescription again and again many times. Not in this homework. The homework here is kind of oversimplified, but later in the course we will do it. So since no one is leaving, it means there is something new here. Okay. So before we went to the presentation session, where each of you were presenting some portion of the background of quantum theory, we stopped at the conversion of time-dependent Schrodinger equations into time-independent Schrodinger equation that doesn't have derivative over time, but it has some potentially it has some derivatives over space or some other operators inside this energy operator. And then there are several, well, we are not going to solve right now because solution of this equation for any practical problem is much more complicated than standard problems in what you had before. It's worth of a couple of hours. So here is an overview. As soon as you have this operator and you formulate this equation, there are several features that you may expect. So that for each Hamiltonian, you'll find several solutions of this equation. So the main feature of this equation is that it has more than one solution. Okay? So you will get so-called eigenenergies, eigenfunction. Energy and function number 1, energy and function number 2, and it can be several of those. One equation, many solutions. Another feature that these functions are expected to be orthogonal. It's your favorite symbol, delta symbol, right?
Green.
No, delta. It is not written here. Never. So it means if you take these functions and integrate over their product, the property of solutions that you get either a 0 or 1. 0 if the functions do not coincide, and 1 if they coincide. And since laziness is the engine of a progress, nothing wrong to be lazy, we save our effort of writing this bracket and denote it by this delta sub a, which means either 0 or 1. Good? I don't care what you're doing right now, but I will comment. Summarize most important things that you believe are important in your notes. Okay, so it was very good. We are looking onto finding solution of time-dependent Schrödinger equation. Who wasn't taking differential equations? One? Who took? Okay. So then I will not tell many new things. So if you have differential equations in very oversimplified ways, it is the solutions of differential equations are often represented in exponential form, one thing. And second, if you have several solutions of the given equation, their summation, if you add together solutions, will be again a solution of the equation. There are exclusions. It is not like absolute truth for the record, but it is a good starting point. So when we were scrolling from complicated time-dependent Schrödinger equation to a little less complicated time-independent, we were splitting the wave function on the product of spatial part that depends on position only, and time part that depends only on time, right? And then the part that depends on time includes the eigen energies of time-dependent Schrödinger equation. And the spatial part does include the eigenfunctions of time-dependent Schrödinger equation. So this is one of the solutions. This is mathematically correct, but scientifically useless. So scientifically useless, well, if you have an idea why it is useless, you can help me. So our goal is to predict future. You cannot predict future if you do not know the past. So generally, if you solve for some propagation time, you need initial conditions. So this general solution doesn't match any initial conditions. So our main goal is to combine this general solution with matching specific initial conditions we start from. And this matching of initial conditions can be achieved by adding together several solutions of such form with some coefficients up front. Right? So by tailoring values of the coefficients, one can match between this solution and initial condition. Waiting, like adding weight to each solution. We can match the initial condition. Orthogonality. Who has fear of this word? Okay. Thank you for being brave and admitting it. Who doesn't have fear of the word orthogonality? Okay, thank you for being brave of not fearing the words. So we already discussed multiply functions, integrate, and get either 0. Right? In some sense, this orthogonality of functions is similar to orthogonality of vectors, but typically your favorite vectors are in 2 or 3 dimensional space. Function is a vector in 1000 dimensional space, or Newton dimensional space. It's like each point of function is kind of projection onto coordinate. So function is a vector of in the space with infinite number of dimensions. Therefore, it's a little crazy and not pleasant for human brain to accept. So instead of being too general, let's make an example. So if you have function 1 equals 1, trivial, function 2 equals x, and let's just multiply these 2 functions and see what we have. 1 is x, dx integral, and minus some limit. So what is integral of x dx?
1. Or sorry, x squared over 2.
Who was your calculus teacher? So what's the outcome?
X squared over 2.
Okay. X squared over 2. And we need to explore it at limits. Okay. So we need to plug in the values of this over 2, right? Who knows the answer? Okay, let's so del squared over 4 over 2 minus del over 2 squared will be the same, right? Del squared over 4. Right? So if the limits on the top and bottom are the same, they will cancel, it will be 0. So you see example how multiplication of 2 functions upon integration gives you 0. So it is, I'm not proving anything, I'm not a mathematician, but I'm showing how product of 2 functions upon integration can give 0. Show that they are in 2-dimensional vector, it would be corresponding to the path for the. Make sense? So we will refer to this property again and again. What else? So it's not the best calligraphy, but here is implementation of the same idea that we have discussed. So we do take the solution of time independent equation, the solution number k, then indices here and there should be the same. Here the time dependent part, exponential minus a bar energy sub k times t. And now we need to add together all of these solutions, but some of the solutions will give a larger contribution to the overall answer, another smaller. In the problems that we are going to solve, typically we will not go into infinite summation. We will just have maybe 2 functions. The rest will be assumed to have 0 conditions. But generally it goes to infinite summation. So, and then each of these terms is multiplied by coefficients, expansion coefficients, C's. So, if you were relaxing and sleeping, if for now you can wake up and I will summarize what we did in form of words. So, solution of time-dependent Schrödinger equation is composed as summation of product of three components. Same as in synthetic chemistry. Mix things, add together, mix, heat, same. There are components to the solution. So, solution of time-independent Schrödinger equation times time-dependent part, which deals with phase accumulation, times expansion coefficient. You need to add infinite number of such products. Any objections or questions right now?
So the last coefficient is like K1, 2, 3, dot, look at CK. The coefficients are, there's like different coefficients. in the
Yes,
solution.
yes. The coefficient in front of each end of each of this product will be different.
Okay.
So it is the only thing that we do not know. Suppose that we won federal grant. It's worth money, and we do not want to deal with math. We just hire a team of mathematicians, and they will solve time-independent Schrödinger equation for us at once, either by pen and paper or by computer. But so we already have these solutions, functions and energies. But we do not have this solution because we need to direct how to develop this answer. So we need to take these two known parts multiplied by the unknown coefficients. So our question that we need to answer in the remaining 22 minutes, where to get these coefficients. So, any ideas? Based on your experience in differential equations.
IVPs, initial values.
Well, it is not values, it is initial conditions. Right. Initial conditions, boundary conditions. So here we need to match initial condition. So in order to make it a well-defined mathematical problem, we do need to state what is our past. We need to find what was the shape of the function at time equals 0. If it is big like true experiment, we need to guess what it is. It was either prepared by cooling down everything or by exciting your system by laser pulse and creating some initial condition. Too complicated. We will deal with it maybe a little later. But in order to have the well-defined problem, we need initial condition. And right now, we are merging together the known solutions of time-independent Schrödinger equation and initial condition. So if someone gives you an exam, asks to solve time-dependent Schrödinger equation, and doesn't give you initial condition, you can protest it. So it's not well-formulated problem. I decline to solve it because it is not a good problem. You have right to do so. So for this sort of equation, you need to have initial condition, or whoever asks you to solve it needs to provide you this initial condition. Okay? So all of the next operation that we are going to commit is to match our past and the future. So we need to choose such coefficients so that this summation of things will reproduce initial condition if you substitute t equals 0 here. This is the only useful. The rest will be mathematical details. Did you get it, or should I repeat? Just give me a sign if you don't mind me repeating it. So, how do we match the initial condition? How do we know that our choice of, so we need to develop an algorithm how to find this C sub k. Suppose we already found these coefficients. How do we know that they were correct? So if the coefficients were correct and we did this humongous summation, then upon substituting time equals 0, this function should be equivalent to this function. So our protocol for predicting future should reproduce the past if we propagate it by 0 seconds forward. Thank you for helping me to formulate it. A protocol to predict future should reproduce past if time increment is 0. Good. There will be no new ideas anymore, but there will be some practice of mathematical things. Take a breath. Let's discuss a little, and then we'll dive into some of the couple of derivations. It's nothing wrong to fear functions because they're multidimensional. But our goal is to find coefficients. Coefficients are just numbers. They're not functions, they're not vectors. We just need to set a set of numbers. So we need to derive an equation that will give us numbers, C sub k, C1, C2, C3. So these coefficients, C capital, will carry information about initial condition, information about initial wave function. But by themselves, they will be not functions, they will be numbers. So our technical goal is to get rid of a function, of a wave function. We need to do some operation that convert this complicated wave function into a number. Okay? It is a technical aspect of the problem. The general goal is just to find such coefficients that would match initial condition. Do you know any operation, well, did you hear today any operation that converts wave function or product of wave functions into a number?
Integral?
Yes. So if you multiply two good wave functions, integrate them, you will get a number. And if they're good functions, you will get either 0 or 1. Why don't we use this skill in achieving our goal of finding exponential coefficients? So wherever we see function that we want to cancel, remove, we can multiply it by another function and integrate. Okay? So it is our hint, our plan. So in I see a wave function, I multiply it by another wave function from the same set, and one needs to take conjugate and integrate. As a result, we remove functions. and deal only with numbers. This is not the answer, but it is kind of a general idea how we can find this series. This slide is a summary. There are no new ideas. Once we recognize everything we discussed right now. So this is our future. Well, not our future of wave summation of three products includes this unknown expansion coefficient. And at time equals 0, our future should coincide to our past. How does this expansion look at time equals 0? Well, it is a silly question of myself because the answer is written in the next slide. What is exponential of 0? Well, yes, you are absolutely correct. So if you place, instead of time, you put here just 0, this time-dependent part will disappear. Right? So at time equals 0, our execution reduces to summation of products of two things: wave functions sub k and expansion coefficient sub k. Superposition of several time-independent wave functions with expansion coefficients. Make sense? No one objects or protests? We have generous 30 minutes to complete this. So, what were we discussing on the previous slide?
How to get rid of wave functions?
Yes, how to omit wave function. Why don't we do a little mathematical experiment and multiply left and right parts of the equation by function of time independent Schrodinger equation and integrate. So if we multiply it here by another wave function and integrate, we will remove both wave functions and we will have only c sub k on the right side. On the left, we will have something non-zero. Okay? Let's try. Summation So what I'm going to try is to multiply this and integrate. Multiply by pi star sub n dx. Okay.
Quick question,
Please.
just to make sure, the pi star and pi and just regular pi are just wave as like a generic notation for wave functions. When you write pi star sub n, that's a notation for a wave function, right? That's what that symbol represents.
If by some reason wave function was found to be non-real, if it has some conjugated, some imaginary components, then star symbol changes sign in front of imaginary components.
Okay, but
Right.
the pi represents a wave function.
Fine.
Phi
Yes,
represents.
yes,
Okay.
it is wave functions of this eigenfunctions of the same Hamiltonian. Which other tricks can I do to simplify our So coefficient is a number, so it doesn't obey any commutation restrictions. So what I can do here is to swap order of this summation and integration. I can put summation k c e. Oh, here it was m, here is k. Dx equals integral of m star psi capital x and 0. Objections?
Why can you do that, did you say?
So when you swap orders of operators, it is dangerous. But if you swap orders of functions of coefficients, it doesn't matter where you multiply it, to the front or to the back. This swap is due to everything here is linear. Who presented about linear operators and all linear? So principle of superposition. Since everything is linear, it doesn't. Well, actually, integration is same as summation, just with very many terms, right? And if you have two summations, you can swap their order. And coefficient doesn't depend on x. Therefore, we can put it a little earlier before integration. Okay? Do you see here any of your old friends? Well, not like photograph from your classmates from high school, but in mathematical sense. There is one of the old friends of you. Do you see? Do you recognize? What is it? Or zero. It is, yes, it is either 1 or 0, and it is delta, right? So due to orthogonality, or orthonormality in more general, product of these two functions, the integration gets this delta. And this stays as it is. You cannot simplify this equation, this left part. So we are almost at the declaration of success. We need, in the remaining 6 minutes, we need one more thing to complete. With what we did. Okay. So on the right part, we have summation of k, c, k, delta, a, n. Is there a way to simplify this? Because of laziness is our main principle, at least mine. Is there a way to write it in a shorter way and simplify it further? So let me open the bracket. So it is equal c. Suppose the c1 times 0. C2 times 0 plus the remaining plus C sub n times 1, C times n squared and 0 So since this delta function will be 0 for each k except k equals n, it will mean c1 plus times 0. And the rest are also 0. So only one coefficient will remain non-zero. So in some sense, if you multiply the progression of coefficients by delta function and make summation, you are parsing only one of these elements of the progression out of this progression. Make sense? So since delta is equal 1 only once, and all other times it is equal to 0, it means out of this summation you pick only one value. Good? Let me, I was feeling irritated. I hated all my instructors before. Until on my 4th year, I decided from, it's not myself, it's one of my instructors, gave simple explanation how to align your mind along this equation. Suppose sleep. And a bunny with 2 ears. And the snake eats the bunny, and they disappear. They kind of cancel each other. So if delta function meets summation, they kind of remove each other, and you change the value of index by the coefficient. We will return to it again and again, and you feel more and more comfortable. It's a standard thing we need to do. Summary, it is just use better calendar. So multiply from left, then we give a swap. We remember the product of wave functions is function. We are good. And due to this, we are so ahead of slides. We need to go further. And then we do have this convolution of two-way functions that provides either 0 or 1 delta function. And then we do this. It's your favorite part of physical chemistry. What do you do in physical chemistry? It's about snakes and bunnies. And it is the thing, what is, if you do not have the C, just summation of delta function, you have just one once, so it will equal once. And good. So on the left part, you have a convolution of the known eigenstate independent linear equation times your initial condition. And on the right, you have just one expansion coefficient. This is really a great success. You can just swap order and say C sub n equals phi sub n times initial condition, right? So it is a protocol how to find expansion coefficients. And you repeat this again and again with each number of n, with each wave function. Do not feel exhausted or irritated with this too much philosophical background. Very soon we will go to practical things and we will implement it again and again. I know that, but you got the answer, right? M equals projection of initial condition onto wave function. And then here is your answer. So the future is equal to product of these three components, or expansion coefficient is this projection. Right? I'm anticipating here will be same. Last slide that we discussed in detail, right? So let me announce completion of the meeting. Looking forward to see you on Wednesday.
We need help with number 3 on the homework. Wednesday night, will we be able to get some?
I will be in the QVB 132 on Wednesday night, and in addition to some MATLAB stuff we can discuss.
Okay.
I'm confident all of you will be able to complete it. I'm happy to help, but it is really doable.
Okay.
I used to